Okay, so we have finished talking about the first part here, which is why is it warming? Yes, it is warming, and the warming is unequivocal. And as we'll talk about in a future class, right, the warming thus far that we've experienced is absolutely unequivocal and exists, and we can observe it, and there's plenty of evidence of it. Very small compared to the warming that we have in the pipeline that we expect to observe in the next in the next few decades. The thing that I want to talk about in this video is this next. Why is it warming? And actually, that is a lie. We've already talked about weather versus climate, so that isn't on there. We're just going to talk about why it's warming. So I want to talk about the greenhouse effect, and also concentrations of carbon dioxide and how they vary in our climate. Okay, so this is a figure that shows back in time concentrations of carbon dioxide. So we abbreviate carbon dioxide as CO2, so carbon dioxide in the air, and we measure in a unit of parts per million, which is ppm. And that is like saying, so 240 parts per million is that if you took a million air molecules, 240 of them would be carbon dioxide. So that's the green line here is showing CO2 in the air, and the purple line here is showing the temperature in Antarctica. So this data is actually taken for what's called an ice core. So before I explain how to read this data, I want to explain what an ice core is. So, and we can actually understand an ice core a little bit based on just living in Albany, New York. So, right, in a really cold place like Greenland and Antarctica, we have these super tall ice sheets that are miles tall. And what has happened is that these are cold places, so cold that the winter snow doesn't melt. So over 1 year's winter, eventually that snow doesn't melt, and it just sort of compacts over time and over time and over time. And trapped inside that packed down snow is actually tiny little bubbles of air that have been trapped in that snow ever since that snow fell. So when we drill down, we drill starting at the top of the Greenland ice sheet and all the way down to the bottom of the Greenland ice sheet, or actually in this case, this data came from Antarctica. We can actually see, in a lot of cases, annual resolution, right? Because we all know that right at the very top, in the summer it doesn't snow, so the very top of that layer of snow gets dirty. So you can kind of, just like tree rings, resolve annual resolution of what the snow looked like. And if we take out little bits of the air, then we can infer a lot of things about what the climate was like. One of them is that we can just directly measure what the concentration of carbon dioxide was in the atmosphere. And another one is that using some techniques that I'm not going to get into, we can actually infer what the temperature of the planet probably was at that time. So that's where this data comes from. And the axes here are a little strange, right? Today starts over here on the right-hand side, and going backwards, the numbers are getting bigger, but we're actually going backward in time. So here's today, there's 100,000 years ago, 200,000 years ago, all the way up to 800,000 years ago. And so the reason I'm putting this up here is that you can see that they go up and down together. So when carbon dioxide is high, that is when the temperature is high. When carbon dioxide is low, that's when the temperature is low. So these two things go up and down together, and they always have, okay? And this interaction that exists between greenhouse gases and temperature is what I want to explain in the next couple of minutes as being the greenhouse effect. All right. So let's talk about what Earth's natural greenhouse effect is. So what I have here is just like a schematic. Here's the sun. The sun's rays are going to pass, oops, too fast, pass straight through the atmosphere and down here and hit the ground. Okay, so the sun emits the kind of radiation that we know to be called visible radiation. We call it visible radiation because our eyes see it. So this is visible radiation. The sun mostly emits visible radiation, and it actually passes straight through our atmosphere for the most part, and it's absorbed by the ground. A lot of people don't know that. Actually, the sun doesn't warm the sky. The sun warms the ground, and then the ground warms the sky. And on a hot summer day, you can really experience this if you walk around outside. Right? The ground will be the hottest spot, and it gets kind of colder the higher up you go. So the sun travels through the atmosphere and it absorbs into the ground. And we can't just have indefinite amount of energy being absorbed by the ground because the ground would just heat up indefinitely. So what the ground does is it takes all of the energy that it absorbs from the sun and it re-emits it back up. Okay. And the cool thing about this is that the kind of radiation, the kind of energy that the ground emits is different than what the sun emits. And this has to do with the fact that the ground is colder than the sun, but we're not going to go into too much detail about that. All I want you to know is that the sun emits this visible radiation, this visible energy, and the ground emits all of the energy that it gets from the sun back up in the form of infrared radiation or infrared energy. Another word for this infrared energy is long wave radiation. So sometimes people will use that word. Infrared radiation is like the kind of radiation that your remote control emits to control your TV. So it's invisible to us, but it still exists. Okay, so in a planet with no atmosphere, this radiation would just travel right back out to space. But we have a planet with an atmosphere. And in particular, our atmosphere is full of these tiny little gases that we call greenhouse gases. So something that you should write down right now, which is the definition of a greenhouse gas, is a greenhouse gas is a gas molecule that absorbs infrared or long wave radiation. So if you need to pause it to write that down, go for it. As the infrared radiation comes out from the ground, it doesn't pass straight back into the atmosphere, back out into space, because it hits our atmosphere with our greenhouse gases first. Okay, so once it hits our greenhouse gas rich atmosphere, there's all sorts of little kind of gray arrow interactions. So it scatters around and hits lots of different greenhouse gases in our atmosphere. But the important thing is what has happened to this energy, this infrared energy, is that some of it goes back up, and that is the energy that goes back out to outer space. Actually, some of it comes back down. Right? The atmosphere isn't like a preferential thing where it has a preferred direction, right? It absorbs a bunch of energy and it emits half of that energy out to space, but half of it comes back down. Okay, so now let's think about the perspective of the ground, okay? The presence of these greenhouse gases in our atmosphere means that now, instead of just having the yellow arrow, so instead of just having one yellow arrow coming back down, we actually have two gray arrows. We have the yellow arrow and the gray arrow coming back down. The effect of that is that there's more energy coming down to the ground and warming the ground and making the planet warmer. So the presence of these greenhouse gases means that more energy is absorbed by the ground, and that more energy is what results in our warmer temperature. So I've written this as Earth's natural greenhouse effect. Here's another cool fact that you should probably also write down. This is not an anthropogenic, right, a man-caused effect. This is the way our Earth naturally behaves. And if we didn't have greenhouse gases in our atmosphere, the temperature of the planet would be around 0 degrees Fahrenheit. Okay, so like 30 degrees colder than freezing. We would have an absolutely frigid place. It would be covered in ice. Probably life, if it ever did evolve, it would have evolved very differently than it did today. It would just be a cold and frigid and awful place that was pretty inhospitable to life. So the greenhouse effect is a good thing, and it is the reason why we get to have the actual temperature of the planet, if you average over the whole globe and the whole year, something like 58 degrees Fahrenheit. So it warms the planet by almost 60 degrees, these naturally occurring greenhouse gases. And the thing that you should write down there is that, right, naturally occurring greenhouse gases warm the planet from about 0 degrees to somewhere around 58 degrees, which is where we are today, or at least where we were 150 years ago. Okay, so what have we done? Well, we have added cars and fossil fuel power plants and all of these carbon dioxide intensive things that are adding a lot of carbon dioxide to our atmosphere. And we are well on our way to doubling the amount of carbon dioxide that's present in our atmosphere above where it was 100, 150 years So we have basically, I'll go back and forth. Here it is. Here's the number of particles that are there. And then when I add this, I want you to see there's more black dots. You see the more black dots? So more black dots are in our atmosphere. And this has basically made our atmosphere more opaque, thicker in terms of letting this infrared radiation escape. So for the ease of instruction, I'm actually going to just move this new layer up here. It's not that in reality we've put a new layer up here. Really, it's just thicker. But I think having it up here makes it a little bit more obvious what's going on, which is that now this arrow here, which used to just travel straight out into space, isn't making it straight out into space anymore because it's getting interfered with by this new layer of carbon dioxide that we've put up into the atmosphere. So you can imagine now, instead of this going straight out to space, well, some of it's going to go straight out to space, but some of it's going to make its way back down to this first layer, and then some of that's going to make its way back down to the ground and cause us to warm up even more. Okay, so Earth's natural greenhouse effect has warmed us by almost 60 degrees. And this anthropogenic, this man-caused extra bit that we've done in the last 100 years is responsible for those next 2 degrees that we have warmed over the course of the last 150 years. And it'll be responsible for an additional, somewhere between 2 and 8 or even 10 degrees Fahrenheit over the course of the next 100 years. And the amount of that warming is really strongly dependent on us, how much we emit into the atmosphere. Okay. So what is a greenhouse gas? So I had you write this down. It's also on the slide, right? A greenhouse gas is any gas that absorbs infrared or long wave radiation, okay? The most important greenhouse gas is CO2, carbon dioxide. You should know that word. You should know the chemical symbol for that word. And we're going to look at the concentrations of that gas in a little bit more detail. Probably the second most important greenhouse gas that you should be aware of is methane. And methane, we don't usually call it methane in this class. We call it natural gas. So a natural gas power plant, the fuel of a natural gas power plant is methane. When you burn gas in a natural gas power plant, what you are intending to burn is methane. Anything else that is in that gas is probably a pollutant is an impurity that you don't want to have in there. Okay, so methane is a really important greenhouse gas that we burn. And actually, when we burn methane, it turns into carbon dioxide. So that's how that can happen. Some issues happen with methane, like say if it leaks into the atmosphere before it makes its way to the natural gas power plant or into your basement to power your boiler, that methane can leak into the atmosphere and be a greenhouse gas just all on its own. Another important greenhouse gas is water. So water vapor in the atmosphere is a greenhouse gas. We don't worry about emissions of water vapor into the atmosphere because we don't really control how much water vapor is in the atmosphere. The humidity of the air depends on its temperature. So right, if we emit water vapor into the atmosphere, that's fine, but that's not what's going to control on a large scale how much water is in the atmosphere. So really, I want to focus in on carbon dioxide, okay? So let's talk about carbon dioxide. So here is some recent observations out in Mauna Loa, Hawaii, so an island out in the middle of nowhere, pretty far from industrial power plants that are sources of carbon dioxide. So, mostly this is kind of like a background level of what carbon dioxide is. And it goes through April 6th of 2020. So it's, I don't know, what is that, the last month or so. And you can see that there's these spikes that go up and down, but really the spikes, we're looking at 415 parts per million, varying just a few parts per million. So we're not varying very much. You can see that there's hourly, daily, and weekly averages in here. So there we are. And there's, little plumes of carbon dioxide rich gas. Or maybe this is when a power plant turned on. And maybe this is sort of waves of plumes that maybe are blowing off of China and making their way into the Pacific Ocean that kind of vary. But on a general level, it's not varying very much over the course of a month. Let's step that out and now look at how much carbon dioxide has varied over the course of the last year. So now we're going April 2019 up to April of 2020. And there's this clear cycle where it's going up and down and up again. So what's going on with this cycle of up and down and up again? So let me get a piece of paper for this and we'll talk about that. So this is where we're at. And so if I kind of pull this up, it looks like the minimum was in October, the maximum was between May and June. So we'll call this kind of May and June and October. And there we go. And this is CO2 concentrations. All right, so what we say is that basically from May into October, CO2 concentrations have not gone up, which might be what you would have expected based on knowing that carbon dioxide is a greenhouse gas and it's going up, but they've gone down. And they've gone down by, I think I have cut off the y-axis here, but the top here is around 415 and the bottom is around 405. So they've gone down, so there's 415 and over here is around 405. So they're going down by, say, 10 parts per million, which is, not a huge amount, but a very noticeable amount, much more than they varied in the last month. So what's causing this? Right? What happens between May and October? This is the growing season, okay? So you, at some point in your life, I promise you, you learned about cycles of photosynthesis and respiration. And what you have learned is that when plants grow, they photosynthesize. So that's via photosynthesis. I misspelled photosynthesis, so you'll have to look that up. THESIS, I believe, which is that they inhale. Now, plants don't breathe, but I'm just going to say that they inhale carbon dioxide. And they exhale. Yeah, that sound familiar? I'm sure you learned it at some point, right? Plants inhale carbon dioxide and they exhale oxygen, which is lucky for us because we inhale oxygen and exhale carbon dioxide. But right here is the growing season. Okay, so as the plants are growing, they are inhaling more and more and more and more CO2 to the point that they're actually making the global concentrations of carbon dioxide go down. Okay, what happens in October? Well, that's when the plants start to die. So I'll kind of extend this out so we can go back up to May. This is, I'll call it the decay season. Winter, whatever it is, right? October happens, the leaves all turn colors and they fall down to the ground, they start to break down. Nothing is growing during this time of the year. Things are just trying to survive during this time of the year. So over the decay season, the opposite of this happens. So they've been inhaling all that carbon dioxide during the growing season, and now during fall and winter, they are decaying. They break down, so they release CO2 like that into atmosphere. Okay, and so this natural process happens every single year where carbon dioxide peaks in like late spring, and then it starts to kind of go down until the plants start to decay again, and then it starts to go up. Okay, so that's the annual cycle of what's happened for CO2 in the last year. Let's go more. And this is observations of carbon dioxide since these observations first started in Mauna Loa, Hawaii back in 1958. So back in 1958, somebody decided to get a can of air and use some spectral techniques to count up how many parts per million of those little parcels of air there was that were carbon dioxide, and they started recording it. We have the longest record of carbon dioxide actually in the world is Mauna Loa, Hawaii, and it started in 1958. So this is what's happened since they started taking observations. And what you can see is we can see these little individual cycles, right? We can see every year it goes up and down and up and down and up and down and up and down, consistent with this natural cycle of plants growing and inhaling carbon dioxide and then decaying and releasing that carbon dioxide back into the atmosphere. But of course, superimposed on top of that is this pretty striking upward trend in carbon dioxide concentrations. So we started in the 50s down here at around 310, and now just a few days ago we were up to around 415. So we've added 100 parts per million in the last 80 years or so, which is a huge perturbation on what is naturally occurring. Okay, so our record of carbon dioxide concentrations that is kind of observed canisters of air that somebody counted up the CO2 molecules ends in 1958. We don't know anything about the air before that. But if you'll remember, we have these ice cores. So those little tiny bubbles of air that are trapped inside the ice on Greenland and Antarctica. So we have a pretty good idea about what CO2 concentrations were going back for a long time. So here we are, we don't get these wiggles anymore when we go back with the ice core data because we just really get a data point for every year. So we know kind of what the average concentration was over that year, and we can go back in time. 1750 is really the beginning of the Industrial Revolution when we developed the steam engine and we started really burning fossil fuels on a large scale. And humans were present in large enough quantities to actually affect the concentration of the atmosphere. So before 1750 or so, everything that's going on with carbon dioxide is natural. And after that, this increase here is what we have done. And you can see that actually it's speeding up really quickly. So the last 50 or 60 years, and actually I think half, a full on half, and this might be a good little factoid to write down. I feel like it's a good statistic to put in a paper is half of the carbon dioxide that we have put into humans have put into the atmosphere has been put into the atmosphere in the last 30 years since 1990, which is pretty crazy. So over the course of a 30-year-old's lifetime, they have emitted half of what we did in all of human history. So that steps us back to maybe 1700, and now we'll step back all 800,000 years, which is the data set that I showed you in the beginning of this video. And you can see that there's these undulations, these cycles in CO2 that are natural. So we have oscillated between warm periods, and that's where the CO2 was the highest, and cold periods, so ice ages that happen on the time scale of every 100,000 years or so. And we actually understand why these happen. The reason that these have happened is because of orbital variations in the Earth. So sometimes the Earth is tilted in a way that makes it capture sun's energy a little bit less efficiently. Sometimes the Earth's orbit is like more of an oval and less of a circle, and all those undulations in Earth's orbit are what have been responsible for these ice age and warm periods that we've had in history. So that's pretty well understood. What I want to point you out is right here, this is what we've done in the last 60 years. Right? At no time in the last 800,000 years did we come even close to what we've done. And even, we had these sort of rapid increases, but these rapid increases were still quite a bit slower than what we've done right now. Okay. Okay, so let's recap what we've talked about with carbon dioxide here. Okay, so carbon dioxide goes up and down due to these natural processes. So the plants die back in the winter, they release their carbon dioxide into the atmosphere as they break down, and the concentrations in the air go up. In the spring and the summer, the plants are growing, so they're inhaling that carbon dioxide, and the concentrations fall. Over the course of a year, and this is an important point, that cycle of respiration cancels itself out. So, plants growing and dying is kind of a zero-sum game if you look over the whole course of the year. Over long time scales, so more than just a year, carbon dioxide is high when temperature is high and vice versa. And this occurs because we have an atmosphere with greenhouse gases in it. And those greenhouse gases are responsible for the greenhouse effect. So when concentrations cause the temperature to rise by trapping heat, we call that the greenhouse effect. Okay, and I think that that is all that I have for this video. So things that I hope you're taking home is kind of a cartoony understanding of what the greenhouse effect is, right? The extra layer of carbon dioxide in the atmosphere means that more of the sun's energy goes back down to Earth, and that's what warms us. And also an understanding of what CO2 does, so why it goes up and down both naturally, so the cycles of photosynthesis, and due to human activities, and that's mostly our burning of fossil fuels.